What if the secrets to understanding the entire universe, from the spinning stars to the quiet whispers of your own soul, were hidden in plain sight, waiting to be unlocked by specific knowledge? What if ancient wisdom, passed down through the Middle Ages, held the keys to this ultimate comprehension, not through magic, but through pure reason and number? Get ready to explore the medieval cosmos, a universe waiting to be mapped by the 7 Quadrivium Arts, a journey through time from roughly 500 to 1500 AD. Number 8. The Great Pursuit of Cosmic Understanding. The medieval world, often painted as a dark age, was anything but ignorant when it came to seeking knowledge. Scholars and thinkers of that era were obsessed with patterns. They saw order in everything, from the smallest grain of sand to the most distant star. This was not a world driven by blind faith alone. It was a world where logic, observation, and deep study were tools for peeling back the layers of reality. They believed the universe was a grand, orderly creation, a perfectly designed machine, and that humans were given the intellect to comprehend its intricate workings. Path to this understanding was laid out through a structured educational system, a system built on what they called the 7 liberal arts. These arts were split into 2 main groups. First came the trivium, focusing on the arts of language and expression, grammar, rhetoric, and logic. These were the foundational tools, teaching students how to read, write, speak, and think clearly. They learned how to articulate ideas, how to persuade, and how to spot faulty arguments. Mastering the trivium was like learning to build the scaffolding for knowledge. It was absolutely essential. But beyond the trivium, after a student had honed their mind and sharpened their communication skills, lay the next more profound level of study. This was the quadrivium. Quadrivium was the gateway to the mathematical sciences, the arts of number and quantity. It was seen as the higher division of the liberal arts because it dealt with the objective, unchanging truths of the cosmos. While the trivium taught you how to understand human thought and expression, the quadrivium taught you how to understand the very structure of the universe itself. These were not just abstract subjects. They were practical paths to seeing the divine order in creation. They were considered absolutely vital for any educated person, especially anyone who hoped to understand theology or philosophy at a deeper level. Quadrivium included 4 specific disciplines: arithmetic, music, geometry, and astronomy. These 4 subjects were linked in a very specific way. Arithmetic was seen as the study of pure numbers as they exist in themselves, without being applied to anything specific. Music, also known as harmonics, was the study of number applied to sound, of numbers in motion, but within a set continuous stream. Geometry was the study of stationary magnitude, numbers applied to space, to shapes and forms that do not change their position. Finally, astronomy was the study of moving magnitude, numbers applied to space in motion, to the movements of celestial bodies over time. Each art built upon the one before it. Arithmetic was the root, the fundamental truth that underpinned all the others. Music showed how numbers created harmony. Geometry showed how numbers structured space. And astronomy showed how numbers orchestrated the dance of the cosmos through time. These were not separate subjects in the way we think of them today as isolated fields of study. They were interconnected paths leading to a single grand revelation. The universe was a symphony of numbers, a perfectly measured and proportioned creation. Medieval scholars believed that by mastering these 4 arts, a person could move beyond the mere appearance of things and grasp the underlying numerical patterns that governed all existence. It was a rigorous, challenging journey, but the reward was nothing less than a deeper understanding of reality, of the divine mind that had ordered everything. Texts they used were ancient, often dating back to Greek and Roman times, preserved and translated by diligent monks and scholars. Thinkers like Boethius, a Roman philosopher from the late 5th and early 6th centuries, were absolutely central to this transmission of knowledge. His writings on arithmetic and music became standard textbooks for centuries, shaping the way generations of students learned about these essential arts. The purpose of the Quadrivium was not just to train skilled technicians or to build fancy instruments. It was about shaping the human mind to think in a specific way, to see the unseen order, to appreciate the beauty of proportion and harmony in the world. It was a spiritual pursuit as much as an intellectual one. The universe was a book written in the language of mathematics, and the Quadrivium provided the alphabet and grammar to read that book. It was a journey from the tangible world of counting and measuring to the abstract world of cosmic harmony and divine truth. This was the grand educational quest, a quest to unlock the secrets of the medieval cosmos. Number 7. Arithmetic Unveiled. Step into the world of numbers as the medieval mind understood them, and you might be surprised. Arithmetic was not just about doing sums or counting sheep. It was seen as the very foundation of all knowledge, the purest of the Quadrivium Arts. This was the study of number in itself, detached from any specific object or measurement. Think of it as the science of pure quantity, of abstract existence. To the medieval scholar, numbers were not just symbols we use for counting. They were fundamental truths, principles that existed independently, shaping the very structure of reality. This idea came from ancient Greek thinkers, especially the followers of Pythagoras, who lived around 500 BC. Pythagoras and his school believed that all is number. This was not just a catchy phrase. It meant they saw numbers as the underlying essence of everything. The relationships between numbers, the patterns they formed, these were considered the ultimate reality, far more real than the fleeting, changing things we perceive with our senses. So, when a medieval student began their journey into arithmetic, they were stepping into a world where numbers held profound philosophical and even spiritual meaning. A central text for this study was Boethius's De Institutione Arithmetica, or On the Institution of Arithmetic. Boethius, writing in the early 6th century, drew heavily from an earlier Greek text by Nicomachus of Gerasa, a Neo-Pythagorean philosopher who lived around the 1st century AD. Boethius's book became the standard curriculum for arithmetic for roughly 1,000 years across Europe. It was copied by hand, studied diligently in monasteries, and taught in early universities. This book laid out the theoretical foundations of number, not just practical calculations. Students learned about different kinds of numbers and their properties. They explored even numbers and odd numbers, perfect numbers, numbers that are equal to the sum of their proper divisors, like 6, which is 1 plus 2 plus 3, and friendly numbers, pairs where each number is the sum of the proper divisors of the other. These classifications were not just mathematical curiosities. They were seen as reflecting deeper truths about the universe. For example, some numbers were considered more perfect or complete than others, reflecting a divine order. Proportions were another massive part of arithmetic. Students learned about various types of ratios, arithmetical, geometrical, and harmonical means. These ratios were not just abstract concepts. They were the key to understanding harmony in music and the movements of celestial bodies. If you understood the proper ratios, you could understand the very balance of the cosmos. For example, the musical octave, the relationship between a note and that same note an octave higher, was found to be a 1:2 ratio. The fifth was 2, 3, the fourth was 3, 4. These exact numerical relationships were seen as evidence of an underlying mathematical order in sound, linking arithmetic directly to music. Medieval arithmetic also explored the concept of numerical symbolism. Certain numbers were believed to hold special significance. The number 3, for example, often symbolized the Trinity. The number 4 might represent the 4 elements or the 4 cardinal directions. The number 7 was frequently associated with creation or completion. These were not just superstitions. They were part of a complex system of understanding that intertwined mathematics, philosophy, and theology. Knowing your numbers was knowing your universe. The study of arithmetic also involved practical skills, though the emphasis was always on the theoretical understanding. Students learned finger reckoning, a system of counting and performing calculations using different positions of the fingers. They also learned about the abacus, a tool for calculations that was widely used before the widespread adoption of Hindu Arabic numerals and the methods we use today. But even with these tools, the focus remained on the inherent qualities and relationships of numbers themselves. Medieval scholars believed that numbers were the language of the Creator. By studying arithmetic, they were learning to read the primary language in which the universe was written. It was a rigorous, demanding subject, requiring intense mental discipline. But for those who mastered it, the reward was a glimpse into the fundamental order of existence. They saw the purity of number as a reflection of divine perfection. Every ratio, every property, every classification of number pointed towards a universe that was not chaotic or random, but instead beautifully, elegantly ordered by simple numerical principles. Arithmetic was the bedrock upon which all higher understanding rested, the pure, unadulterated truth of quantity waiting to be discovered. Number 6. The harmony of music. Now we move from pure number to number in motion, specifically the motion of sound. This is where the study of music, or harmonics as it was often called, entered the quadrivium. Forget pop songs or catchy tunes. Medieval music study was not primarily about performance or composition in the way we think of it today. It was a profound intellectual pursuit, a deep dive into the mathematical ratios that create harmony. It was about understanding the cosmic symphony, the way numbers ordered sound, and by extension, the entire universe. Just like arithmetic, the roots of this study stretched back to ancient Greece, with Pythagoras again taking center stage. Legend has it that Pythagoras discovered the mathematical basis of musical intervals by listening to the sounds of hammers striking an anvil or observing the lengths of vibrating strings. He found that simple, whole number ratios produced consonant, pleasing sounds. For instance, having a string's length produces a note an octave higher, a 1:2 ratio. Dividing a string by a third gives a perfect fifth, a 2:3 ratio. A perfect fourth comes from a 3:4 ratio. These discoveries were revolutionary. They showed that something as seemingly intangible as sound was governed by precise mathematical relationships. Boethius's De Institutione Musica, or On the Institution of Music, became the undisputed authority on this subject for centuries. Copied and recopied, this text was the primary way medieval scholars learned about the mathematical theory of music. Boethius, drawing from Greek sources like Ptolemy and Nicomachus, categorized music into 3 types. The first was musica mundana, the music of the spheres. This was the most profound type, the harmony created by the perfectly proportioned movements of celestial bodies. Planets, stars, and orbits were believed to move in specific mathematical relationships, generating an inaudible but perfect cosmic melody. Humans could not hear it directly because they were part of it, steeped in its continuous presence since birth. The second type was musica humana, the music of the human being. This was the harmony of the body and soul, the perfect balance between the different elements and temperaments within a person. A healthy person, both physically and mentally, was considered to be in tune, a living example of balanced ratios. Illness, on the other hand, was seen as a disharmony, a breakdown in these internal proportions. This connected musical theory directly to medicine and philosophy. The third type was musica instrumentalis, the music made by instruments and voices. This was the only type of music that was actually heard by humans. But even this observable music was seen as a pale reflection of the grander, cosmic and human harmonies. Studying musica instrumentalis meant understanding how to construct instruments correctly, how to tune them, and how to combine notes to create pleasing sounds based on those divine ratios. It wasn't about personal expression. It was about replicating the mathematical order found in the universe. Students of music learned about scales, modes, and intervals, all understood through their numerical relationships. They learned which intervals were consonant, pleasing, like octaves, fifths, and fourths, and which were dissonant, harsh, needing resolution. The beauty of music was not subjective. It was objective, derived from the mathematical purity of its ratios. A piece of music was considered beautiful because it reflected the inherent numerical order of the universe, not because it evoked a particular emotion in the listener. The ethical dimension of music was also a significant part of its study. Following Plato, medieval thinkers believed that different musical modes or harmonies could influence a person's character or the character of a society. Certain modes might inspire courage, others might lead to softness or depravity. This meant that the study of music was not just an intellectual exercise. It was a moral one, a way to understand how sound could shape the very soul. A well-ordered society, like a well-tuned instrument, reflected cosmic harmony. Monks and scholars spent countless hours studying these mathematical principles, often using monochords, simple instruments with a single string, to demonstrate the precise ratios of intervals. They would meticulously measure string lengths, proving the mathematical relationships that Pythagoras had supposedly discovered. This hands-on numerical exploration reinforced the idea that number was everywhere, even in the fleeting vibrations of sound. The study of music in the Quadrivium was therefore a profound intellectual and spiritual journey. It was about discovering the invisible order that connects sound to number, the human body to the cosmos, and the entire universe to its divine source. By understanding the harmony of sound, medieval scholars believed they were taking a step closer to understanding the ultimate harmony of creation. It was a rigorous mathematical discipline that elevated music far beyond mere entertainment, placing it squarely at the heart of cosmic understanding. Number 5. Geometry's spatial secrets. Having explored numbers in their pure form and in the movement of sound, we now turn to numbers in space. This is the domain of geometry, the third art of the Quadrivium. Geometry was known as the science of stationary magnitude, the study of fixed shapes and sizes. It was the pathway to understanding the structure of the world, from the smallest architectural detail to the vast expanse of the earth itself. While arithmetic dealt with abstract numbers and music with vibrating numbers, geometry brought numbers into the tangible world of lines, planes, and solids. The undisputed master text for geometry was Euclid's Elements, written around 300 BC. This collection of 13 books was arguably the most influential mathematics textbook of all time, serving as the standard for geometry for over 2,000 years. Medieval scholars studied Latin translations of Elements, meticulously working through its definitions, axioms, postulates, and propositions. Euclid laid out geometry as a logical system, starting from basic truths and building up to complex theorems. This rigorous, deductive reasoning was highly valued as a way to train the mind. Students of geometry learned about points, lines, angles, triangles, circles, and polygons. They explored concepts like congruence, similarity, and proportion in spatial figures. The methods were often practical, involving the use of a compass and straight edge to construct shapes and prove theorems. This was not just about memorizing facts. It was about developing a deep understanding of logical proof and spatial relationships. One significant aspect of geometry in the medieval world was its connection to understanding the physical world. Scholars applied geometrical principles to measure land, to survey fields, and to understand distances. The discipline provided the tools for creating maps and understanding geography. The Earth was understood to be a sphere, a perfect geometric form, and geometry allowed scholars to conceptualize its circumference and position within the universe. Ancient Greek measurements of the Earth's circumference, like those by Eratosthenes, which were remarkably accurate, demonstrated the power of geometric methods. Sacred geometry was another vital aspect. The medieval period saw the construction of magnificent cathedrals and churches, and these structures were often designed with precise geometric principles. Builders and architects used ratios and shapes derived from geometric theorems, believing that certain proportions were inherently beautiful and reflected divine order. The use of circles, squares, and equilateral triangles, and their relationships to each other was seen as a way to imbue the architecture with spiritual meaning. A perfectly constructed arch, or a precisely proportioned nave, was not just an engineering feat. It was a visible manifestation of cosmic harmony, reflecting the divine mind that had ordered the universe. The study of Platonic solids was also crucial. These are the 5 regular polyhedra: the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Plato, in his dialogue, Timaeus, associated these solids with the classical elements, the tetrahedron with fire, the cube with earth, the octahedron with air, the icosahedron with water, and the dodecahedron with the cosmos itself. Medieval scholars continued this tradition, seeing these perfect geometric forms as fundamental building blocks of the universe. Another example of numbers manifesting in physical space. Geometry also served as a bridge between abstract numerical theory and the observable world, allowed scholars to visualize the relationships they had studied in arithmetic and music. Patterns of sound described by numerical ratios found their visual representation in geometric shapes. The movements of celestial bodies, which would be studied in astronomy, could be understood as complex geometric paths. The teaching methods were rigorous. Students would copy out Euclid's proofs, drawing the diagrams carefully and repeating the logical steps. This was an exercise in precise thought and meticulous attention to detail. The ability to reason geometrically was considered a mark of a truly educated mind, capable of discerning order in the material world. By mastering geometry, medieval scholars believed they were gaining insight into the unchanging perfect forms that underpinned the visible world. They learned to see the world not as a chaotic jumble of objects, but as a meticulously designed creation, structured by elegant mathematical principles. Every shape, every angle, every proportion pointed to an underlying order, a silent testament to the precision of the cosmos. Geometry was not just about measuring things. It was about measuring the divine plan, about seeing the universal blueprint in the lines and forms of existence. Number 4. Astronomy's celestial dance. We have journeyed from pure numbers to numbers in sound, to numbers in stationary space. Now, for the pinnacle of the quadrivium, we arrive at astronomy, the science of moving magnitude. This was the study of the heavens, the grand celestial ballet of stars and planets. To medieval thinkers, astronomy was not just about observing distant lights. It was about understanding the cosmic clockwork, the precise mathematical movements that governed time, seasons, and even, it was believed, earthly events. The ultimate authority in astronomy for the medieval period was Claudius Ptolemy, a Greek astronomer and mathematician who lived in Alexandria in the 2nd century AD. His monumental work, the Almagest, meaning the greatest book, was a comprehensive treatise on astronomy that summarized centuries of Greek astronomical knowledge, presented a geocentric model of the universe with the Earth at the center, surrounded by a series of concentric spheres carrying the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the fixed stars. This model, though later superseded by the heliocentric view, was incredibly sophisticated and mathematically detailed, perfectly aligning with the medieval worldview of an ordered hierarchical cosmos. Students of astronomy immersed themselves in the intricacies of Ptolemy's model. They learned about epicycles and deferents, complex geometric constructions used to explain the seemingly erratic movements of planets as they appeared from Earth. Planets were observed to sometimes move backward in their paths across the sky, a phenomenon known as retrograde motion. Ptolemy's system, though intricate, provided a mathematical way to predict these movements with remarkable accuracy. This was a triumph of applied geometry and arithmetic. Observing the heavens was a crucial part of astronomical study. While medieval instruments were not as powerful as modern telescopes, scholars used tools like armillary spheres, which represented the celestial spheres, and astrolabes, handheld devices used for measuring the altitude of celestial bodies and solving various astronomical problems. These instruments were both practical tools for observation and beautiful examples of applied mathematical knowledge. Astronomy was deeply connected to timekeeping. The movements of the sun, moon, and stars were the ultimate basis for calendars, marking the passage of days, months, and years. Knowing the precise timing of equinoxes and solstices was essential for agriculture, religious festivals, and navigation. Sailors and travelers relied on the stars for guidance, using their positions to determine direction and approximate location. Beyond mere observation and calculation, astronomy held profound philosophical and theological significance. Perfect, unchanging circular motions of the celestial spheres were seen as reflections of divine order and perfection. The heavens were considered incorruptible, a realm of pure mathematical harmony, contrasting with the changing, imperfect earthly realm. The regular, predictable dance of the cosmos was evidence of an intelligent, powerful creator. For many medieval thinkers, astronomy was inextricably linked with astrology. While modern science separates these two, in the medieval period, they were often considered two sides of the same coin. The belief was that the positions and movements of celestial bodies exerted an influence on earthly events, human temperament, and even individual destiny. An astronomer would not only calculate the precise positions of the planets, but also interpret their potential effects. This was not always a deterministic view. It was often understood as a predisposition or an influence, rather than an absolute fate. This connection made astronomy a subject of immense practical relevance for rulers, physicians, and even ordinary people seeking guidance. An astronomer might be consulted to determine the most auspicious time for a coronation, a battle, or even a wedding. A physician might consult celestial charts to understand the bodily humors of a patient and choose the best time for treatment based on the planetary alignments. This intricate web of belief meant that the careful mathematical work of calculating planetary positions had direct implications for daily life and understanding the natural world. The study involved not just understanding the models, but also the historical observations that supported them. Scholars learned about the great astronomers of antiquity, appreciating the continuity of knowledge. They understood that their own observations built upon centuries of careful work by those who came before them. Astronomy in the Quadrivium was therefore the culmination of numerical study. It applied the principles of arithmetic to the grandest scale, used the harmonies of music to describe the cosmic symphony, and relied on geometry to map the vast distances and intricate paths of celestial bodies. By mastering astronomy, medieval scholars believed they were gaining insight into the ultimate clockwork of creation. Witnessing the divine intelligence in action, through the ceaseless perfect motions of the heavens. It was a science that brought together all the other numerical arts, revealing a universe of awe-inspiring mathematical order. Number 3. The quadrivium's purpose. You have now seen the individual lights of arithmetic, music, geometry, and astronomy. But how did these 4 distinct disciplines, each with its own ancient roots and rigorous methods, fit together? Why were they grouped as the quadrivium? And what was their ultimate purpose in the grand scheme of medieval education? The answer lies in a deeply held belief that these 4 arts collectively offered the most profound path to understanding the divine order of the universe. The medieval worldview was profoundly ordered. Scholars believed that the universe was not a chaotic accident, but a meticulously designed creation, perfect in its structure and function. This order was seen as a reflection of the Creator's mind, and the language in which this order was written was mathematics. Quadrivium, therefore, was not merely a collection of subjects to pass exams in. It was a toolset for deciphering the very blueprint of existence. Arithmetic, as the science of pure number, was the starting point. Provided the fundamental concepts of quantity and ratio, the building blocks. Without a solid grasp of abstract numbers, the other arts could not be truly understood. It taught the student to think in terms of immutable truths and universal principles that existed independently of the physical world. It was the alphabet of cosmic understanding. Music, or harmonics, immediately applied these numerical principles to sound. It showed how simple whole number ratios created beautiful consonant harmonies. This was not just about the sounds heard by human ears. It extended to the profound concept of musica mundana, the inaudible but perfect harmony of the celestial spheres. By studying music, the student learned that order and proportion were inherent in motion and vibration, revealing a layer of cosmic beauty that transcended the visible. Geometry then moved these numerical principles into the realm of stationary space. It demonstrated how lines, shapes, and solids were constructed according to precise mathematical rules. From the perfect circle to the complex patterns of sacred architecture, geometry revealed the visible manifestation of divine order. It allowed the student to understand the physical world as a reflection of perfect, unchanging forms, demonstrating that design was everywhere, from the smallest diagram to the grandest cathedral. Finally, astronomy brought all these threads together by applying numerical and geometric principles to the most awe-inspiring display of order: the movements of the celestial bodies. Complex paths of planets, the cycles of the sun and moon, and the positions of the stars were all understood as a vast, intricate, and perfectly calibrated mechanism. Astronomy was the ultimate demonstration of numbers in motion through space and time, showing the universe as a grand, living clockwork, eternally moving with mathematical precision. Thus, the quadrivium presented a unified vision of knowledge. It moved from the abstract to the concrete, from the static to the dynamic, always returning to the fundamental truth of number. The progression was deliberate and logical. A student would master numbers in themselves, then in sound, then in space, and finally in the grand moving spectacle of the cosmos. Each step deepened the understanding of the one before it and prepared the mind for the next. The goal was not just intellectual mastery. It was about cultivating a profound appreciation for the order and rationality of creation. By understanding the mathematical structure of the universe, scholars believed they were glimpsing the mind of the Creator, understanding the wisdom and beauty inherent in the cosmic design. This understanding was seen as a prerequisite for higher theological or philosophical contemplation. How could one truly understand divine wisdom without first understanding the mathematical principles that governed the very fabric of his creation? The quadrivium trained the mind to seek patterns, to understand cause and effect, and to appreciate the elegance of mathematical solutions. It fostered a sense of awe and reverence for the universe's intricate design. It was a rigorous intellectual exercise, but it was also a spiritual journey, guiding the student towards a more profound connection with the universal order. This interlinked nature of the quadrivium meant that these subjects were not taught in isolation. A lesson on planetary movements in astronomy would naturally invoke discussions of geometry for their paths and arithmetic for their speeds and distances. Concept of the music of the spheres directly linked astronomy back to harmonics and arithmetic. This holistic approach ensured that students saw the connections, the underlying unity of all knowledge. The quadrivium was the master key, unlocking the numerical secrets of the medieval cosmos. Number 2. The roots of ancient wisdom. The ideas that formed the quadrivium were not inventions of the medieval period. They were precious legacies meticulously preserved and transmitted from ancient civilizations, particularly from the Greeks and Romans. For medieval scholars, looking back to these earlier periods was not a step backward. It was an act of reverence for the wisdom of the ancients, a commitment to building upon the intellectual foundations laid by brilliant minds centuries before them. The most prominent figures in this transmission of knowledge were the Greek philosophers and mathematicians. Pythagoras, living in the 6th century BC, was legendary. Even if many stories about him are apocryphal, his school's central idea that all is number profoundly shaped the understanding of the quadrivium. His disciples were credited with the discovery of numerical ratios in music, forging the link between arithmetic and harmonics that became central to the medieval curriculum. Pythagorean fascination with perfect numbers, numerical symbolism, and the harmony of the spheres resonated deeply with the medieval desire to find order and meaning in the universe. Plato, in the 4th century BC, further elevated the status of mathematics. He believed that the study of arithmetic, geometry, astronomy, and harmonics was essential for training the mind to grasp eternal, unchanging truths. He famously stated that, "Let no one ignorant of geometry enter here, above the entrance to his academy." For Plato, these mathematical disciplines purified the soul and prepared it for philosophical contemplation. His concept of the Platonic solids, associating perfect geometric forms with the elements and the cosmos, directly influenced medieval geometry and cosmology. His ideas about the ideal, unchanging forms reflected in the visible world were echoed in the medieval view of numbers as perfect archetypes. Euclid, active around 300 BC, produced his Elements, a work that established the gold standard for deductive reasoning in geometry. His systematic presentation of axioms, postulates, and theorems was not just a textbook. It was a model of logical thought that informed the entire approach to scholarship in the Middle Ages. The rigorous structure of Euclid's proofs became a benchmark for intellectual clarity and precision across all disciplines. Medieval students, poring over his diagrams and propositions, were learning how to think clearly and logically, skills essential for any serious study. Claudius Ptolemy, the great astronomer and geographer of the 2nd century AD, consolidated centuries of Hellenistic astronomical observations and theories into his Almagest. His geocentric model of the universe, with its complex system of epicycles and deferents, became the undisputed framework for understanding the cosmos for over 1400 years. His work demonstrated the power of mathematics to predict and describe celestial movements, providing a detailed, calculable picture of the heavens that satisfied both scientific inquiry and theological convictions about an ordered creation. Beyond these giants, there were numerous other Greek scholars whose works contributed to the rich tapestry of the quadrivium. Nicomachus of Gerasa, a Neo-Pythagorean mathematician from the 1st century AD, wrote an introduction to arithmetic that was a key source for Boethius. Pappus of Alexandria, in the 4th century AD, preserved much of earlier Greek mathematics in his collection. These texts, often fragmented or difficult to access, were sought out and translated by diligent scholars. The Roman contribution was primarily one of transmission and synthesis. While Roman thinkers generally excelled in practical application rather than pure theory, figures like Marcus Terentius Varro in the 1st century BC listed the liberal arts, including the 4 mathematical ones, as foundational to education. However, it was Anicius Manlius Severinus Boethius, living in the late 5th and early 6th centuries, who played the most pivotal role in bridging the gap between antiquity and the early Middle Ages. Boethius, a Roman philosopher and statesman, embarked on a monumental project to translate and comment on all the works of Plato and Aristotle into Latin. Though he did not complete this ambitious task, his translations and original treatises on the Quadrivium Arts were hugely successful. His De Institutione Arithmetica and Institutione Musica became the standard textbooks for these subjects throughout the Middle Ages. His clear, systematic presentation of Greek mathematical and musical theory, translated into accessible Latin, ensured that these vital branches of knowledge were preserved and continued to be studied in the Latin West during a period of significant cultural upheaval. Monasteries played an absolutely crucial role in this process. Monks diligently copied these ancient texts by hand, preserving them through centuries where books were incredibly rare and precious. Later, with the rise of medieval universities in the 12th and 13th centuries, these texts formed the core of the arts curriculum, educating generations of scholars, theologians, and thinkers. The Quadrivium was therefore a magnificent inheritance. It was a continuous thread of mathematical and cosmic understanding stretching back to the earliest known intellectual traditions. Medieval scholars saw themselves as inheritors of this ancient wisdom, not as innovators building from scratch. They were interpreters and custodians, striving to understand and apply these timeless principles to their own ordered world. Quadrivium was truly a testament to the enduring power of ancient thought, a key that continued to unlock the secrets of the cosmos for centuries. Number 1. The 7 liberal arts unify. We have explored the 4 pathways of the Quadrivium: arithmetic, music, geometry, and astronomy. But remember, these were only half of the story. They were the higher division of a complete system known as the 7 liberal arts. Understanding the Quadrivium fully requires glimpsing its connection to the other 3 arts, the trivium. The medieval cosmos was not just about numbers and stars. It was also about words, logic, and the very structure of human thought. The 7 liberal arts comprised the standard curriculum in medieval schools and universities, beginning around the 5th century and flourishing throughout the Middle Ages. They were considered liberal because they were the studies fit for a free man, preparing an individual for civic life, moral understanding, and ultimately for the contemplation of higher truths. These arts were a holistic system for cultivating a well-rounded and intellectually disciplined mind. First came the trivium, the 3 arts of language and expression: grammar, rhetoric, and logic. These were considered foundational, the entry point to all further knowledge. Without mastering the trivium, a student would struggle to articulate ideas, understand complex texts, or engage in rigorous debate. Grammar was the art of speaking and writing correctly. It involved studying Latin, the language of scholarship, and the church learning, its rules, syntax, and vocabulary. It was about developing precision in language, understanding the building blocks of communication. A student of grammar learned how to structure sentences, how to decline nouns and conjugate verbs, ensuring clarity and correctness in their expression. This was the key to unlocking the vast library of ancient and theological texts. Rhetoric was the art of persuasive speech and writing. It taught students how to construct compelling arguments, how to present ideas effectively, and how to sway an audience. This involved understanding different forms of discourse, identifying figures of speech, and mastering the art of eloquent delivery. Rhetoric was vital for public life, for legal arguments, and for preaching. It was about packaging ideas in a way that resonated with others. Logic, or dialectic, was the art of reasoning and critical thinking. It taught students how to construct valid arguments, identify fallacies, and engage in philosophical debate. Students learned about syllogisms, definitions, classifications, and methods of proof. Logic was the ultimate tool for discerning truth from falsehood, for moving from observation to sound conclusion. It was the training ground for the intellect, preparing the mind for rigorous inquiry. Only after a student had mastered the trivium were they deemed ready for the quadrivium. The trivium provided the tools for inquiry: how to read, how to speak, how to think. Quadrivium then provided the objects of inquiry, the mathematical truths that underpinned the universe. The connection between the two groups was profound. The trivium taught you how to understand. The quadrivium taught you what to understand at the deepest level. You needed logical rigor from the trivium to follow the proofs in Euclid's Elements. You needed the precision of grammar to comprehend Boethius's intricate arguments about numbers and music. You needed rhetorical skill to present your astronomical findings or to explain the harmony of the spheres. The ultimate goal of this entire system was to lead the student towards higher philosophical and theological studies. For medieval scholars, the liberal arts were not ends in themselves, but stepping stones to understanding the divine. By learning the structure of language, the methods of reason, and the mathematical order of the cosmos, a student was prepared to contemplate the ultimate truths of God, creation, and humanity's place within the grand design. The 7 liberal arts were seen as mirrors, reflecting the divine intellect. Trivium reflected the order of human thought and expression, while the quadrivium reflected the order of creation itself. Together, they formed a complete intellectual journey, guiding the student from the tangible world of words and arguments to the abstract realm of numbers and cosmic harmonies. This educational framework shaped the minds of generations of scholars, saints, and leaders throughout the medieval period. It was a rigorous, integrated system that sought to provide a comprehensive understanding of reality, both human and divine. Quadrivium, with its focus on numbers and the cosmos, was the highest peak of this intellectual mountain, offering the clearest view of the intricate, beautiful, and mathematically ordered universe. It was the final key, unlocking the secrets of the medieval cosmos.